Let's get started. So we have our afternoon keynote. Thank you so much for attending us. So Professor Jang Kim is a well-known, is a currently full professor in the School of Electrical Engineering at KAIST in Daejeon, Korea. Jang Kim received his PhD from Stanford University and MS from Cornell University. His research interests include computer architecture, interconnection networks, security, and mobile systems. He has received a Google Faculty Research Award, Microsoft Asia New Faculty Fellowship, and is listed in the Hall of Fame for ISCA Micro and HPC. He has also worked on the design of several microprocessors at Intel and Motorola. Thank you so much.
Thank you for the introduction. And thank you for having me here. I was thinking of a good title to put for my talk. And I was, as usual, I was late in terms of submitting my abstract. And it was going to be on topic of GPUs and bandwidth, and I was thinking of bandwidth in terms of challenges and opportunities, but that was too similar to Jan's keynote, so I was too late with that. And I was really confused in terms of what my talk title should be, so that's where confusion comes in. But I think that's sort of representative of what it is that I wanted to talk about. One thing that's different, I think, about my talk versus maybe I'll compare it to Jan's earlier keynote, is that most of these talks talk about some of the great work that you've done and sort of highlight the key ideas there. I'm going to do the opposite. I'm going to talk about one of the works that we did a while back and talk about what was wrong with it. So I'll speak on my behalf. I won't speak on behalf of the co-authors of that work, but I think there were some interesting things to be learned. And so I'll talk a little bit about that and sort of the various different insights that you can gain. So it won't be anything new in terms of new ideas or new microarchitecture. So if this was a paper, it would be rejected right off the bat. But I think there are a lot of small insights here and there to be gained, especially if you are working in area of GPGPUs. So with that, I guess I should credit my students for the work because they're the ones that actually do the work and generated the plots. Before we get started, here's just this short summary of what this talk will be about. I think if you travel abroad and you have real good food, you sometimes wonder what's in there. And sometimes it's better that you don't know what's inside that. You just sort of enjoy the food. Even if you're eating at home, you sort of have to know what's inside. So I think people are being a lot more conscious of what it is that you're eating. That's my question to you, is that a lot of you work in the area of GPUs, and then you have to realize that you're using on-chip bandwidth for whatever it is that you're doing. And whether you like it or not, it's a real thing. Now, the question is, do you really know what you're doing? Or do you really know what you're assuming? So just to get things motivated, these are no two particular papers, but just the two papers that came up if I Google for GPGPU sim. And if you look at that particular line, so you probably can't see, but it's not really important here, is that everyone makes some assumptions about the interconnect. And there's nothing wrong with that assumption, but the question is, do you really understand that? Sorry, I'm going to pick on Jan's keynote earlier. He talked about certain components that he was adding, and he said it was going to take 40 cycles. I remember that numbers exactly, because I'll bring that up again. Because based upon what you're seeing in real on-chip interconnects, that 40 cycle can have an impact. Sometimes you can sort of rub it under the rug, sort of sweep it under the rug, sorry. But sometimes it's not. Sometimes it is more, it will have more of an impact. So that's where hopefully you'll be able to gain some insights in terms of how on-chip bandwidth impacts overall system performance. So with that, I don't think I need to talk a whole lot about this service line. Everyone knows that the bandwidth compute of GPUs are increasing. I think from my perspective, at least from this talk's perspective, there are two things. One is a top line where you have the number of cores on a GPU is increasing. And at the same time, the memory partitions or the number of partitions on a chip is also increasing. So the job of the on-chip bandwidth is that we need to interconnect them together. right? So all of you have seen a picture like this. And then there's the cores or the SMs on one side, the memory partitions on the other, and then the interconnect. So when people talk about on-chip bandwidth, on-chip interconnect, they think of this sort of a cloud that I've shown here on the right. One small insight that I hope you take away is that that is physically the on-chip interconnect, but it's really this cloud. So if you see the difference, there's a subtle difference, but I just sort of made it a slightly bigger. Now, as someone that has worked on interconnection networks, I think it's the most important thing. That's a biased view, but no one really cares about interconnection networks. People care about the system. That's what you're paying for. So having a very fancy interconnection network, that's great, but it's only great if that impacts the overall system performance. So that's something to keep in mind as well. So again, this is what we'll be talking about, and this is where I sort of change gears and talk about a work that we did almost 13 years ago. So this is one of the first work that I did after my PhD. And the story goes, I think it was 2008, ISCA, Beijing. Tor student was sort of giving a talk at one of the workshop on GPGPU Interconnect, and I thought it'd be a great thing if I worked on that. So I sort of dragged Tor into this, and we did this work on looking at the design space of on-chip interconnect for GPGPUs. So there's nothing wrong with that. I had no clue what GPGPUs were back then, but Tor knew, and he had designed the GPGPU sim simulator, so I thought it'd be a great match. We finally did get a paper published, and there was a lot of things that went well, and then there were things that did not. So I'll talk a little bit about that. This is one of the pretty plots that the student generated as part of the paper. It looks at, there's a couple of things I thought that's important here, is that we didn't look at interconnect performance, we looked at overall performance. And we didn't look at interconnect cost, we looked at the entire system cost. I thought those are important things. And then we wanted to strive towards finding what was a balanced interconnect. So that's great. This is the part I think where we got it wrong. I'll be honest, we got it wrong in many different ways. So we had this plot and we talked about the communication patterns. And we even coined a cute name for this. We called it a many to few to many traffic. Now, there's nothing wrong with that because there's many cores injecting traffic towards a few of the memory controllers. Now, the memory controllers are going to be, in many cases, accessing the memory, so they generate these replies that have to come back out to the many cores. So there is nothing wrong with that, but the subtle assumption that we made sort of skewed the results in a way that changes what you would expect in terms of on-chip interconnect. So just to summarize, I think this is sort of the good part of the work that we did back then. Again, this is my own opinion, but this is one of the first times that people started looking at high bandwidth networks, right? This was not a multi-core network on chip, so you do require high bandwidth, high throughput. We did look at sort of trying to come up with a balanced network. I think a lot of, I don't want to say a lot, some issues on some of the works is that they start off with this sort of huge fat networks, and then they try to do all sorts of optimization, right? That's obviously that has some value there, but it's your starting point is not necessarily the most optimal point. So we focused on sort of the optimal balanced networks. And just like there are domain-specific accelerators architectures out there, I think one of the things that we need to look at is sort of what domain-specific networks are. And this was, I thought, was a starting point. So again, something like this, I think, was the right thing to do. The part that I believe, again, this is my own opinions, but the things that we didn't do well are some of the bandwidth assumptions. So I'll talk a little bit more about what that is. I sort of get embarrassed now when people cite our work and say that 2D meshes are used in GPGPUs. Yeah, it was a micro paper, so it's a good paper to cite, but we used a 2D mesh and no one really uses a 2D mesh in GPGPUs. So that's something to think about. Our assumption of a 2D mesh led to the problems that we were solving back then. So that is something that I'll talk a little bit more about. Again, maybe we focus too much on being domain specific in that work. So having said that, just a quick tutorial on bandwidth interconnection networks. You'll find this in any textbook, but the two metrics that people care about are latency and bandwidth, right? And here's sort of a mathematical definition of what a bisection bandwidth, right? You divide the system in two halves and you cut it, and the minimum number of channels, that's how bisection bandwidth is defined. I'm not here to say that that metric is wrong. That is one of the more important metrics when designing interconnection network systems. When we worked on sort of the high performance computing, the supercomputer sort of networks, this is the most important parameter of the network. This is what customers will care about when they're purchasing their systems. So having had that background, I try to apply the same thing for the GPGPUs. So this is our system. This is our block diagram earlier. And if you wanted to know what the bisection bandwidth, you cut it in half, and that's the red line there. So we looked at what the bandwidth requirements are. We looked at what the bisection bandwidth was, and then we sort of optimized the bisection bandwidth accordingly. Right. So again, and this is what that work was sort of about. Now, so far, there's nothing wrong with that. Right? Again, trying to optimize the bisection bandwidth, ensuring that you have sufficient amount of bisection bandwidth is obviously an important thing. But that's assuming sort of a monolithic multi-core sort of an organization that you see on the right, which is not the case for these sort of GPUs because of literally of the traffic that we're assuming, which is from the cores to the memory. So to better understand that, I'm sure all of you have seen this in your computer architecture class. You have what's called a memory hierarchy. I was thinking, you know what, there should be a bandwidth hierarchy. So this is sort of what I sort of tried to sketch out. So you have the memory bandwidth, which is obviously the most costly component, but it should be the least amount of bandwidth you provide. And then below that, you have the on-chip cache bandwidth, for example, the L2 bandwidth. And then below that, you have the NoC bandwidth. So in general, I believe the bandwidth hierarchy should be that the NoC bandwidth should be the cheapest, but at the same time, it could provide the most bandwidth. So that's the picture that I have in mind. And the last thing you want to do is design something like this, right? You do not want to work on a network architecture and saying, you know what, I have an NoC bandwidth bottleneck and I'm trying to solve that. And if your assumption is that diagram on the right, I think you have the wrong starting point. Now, I would think maybe something like the diagram on the right is a much more balanced organization, right? You might have some wiggle rooms for the NoC or DL2, but that should be sort of much more balanced organization in terms of the bandwidth and cost, right? One thing is that people talk about, well, certain things are free. Well, nothing comes for free. Even on-chip bandwidth, someone has to pay the price, cost in some way. And a design like something on the right is what should be targeted. And if you need additional bandwidth to cover for the more expensive bandwidth, maybe something on the left is the right thing to do. Now, having said that, this is the part where we got it wrong here. We talked about the many to few to many sort of a traffic pattern, but you see on the right, we identified the bottleneck here as sort of this point here on the right. The bandwidth from the memory back into the core, we argued that it was the bottleneck. Now, that made a lot of sense because there are a few of the memory controllers and they're injecting these bigger packets. For example, most of the traffic is going to be reads. So the traffic coming out will be those sort of big, large, cache lines type packets. So we thought that was the bottleneck. But by making that assumption, we actually created an artificial bottleneck in our system. We were not providing enough bandwidth at the interface of the network on chip compared to the memory system. Now, just to convince you that I'm not lying here, these are some very simple synthetic sort of tests that my students ran on a real system. So one on the left is a Maxwell, which is an old system, and then a Volta system. So on the x-axis is the number of CTAs that we're running on each core. So it's just a very simple synthetic workload. Y-axis is the bandwidth that's measured. So the green line is the maximum memory bandwidth supported by that particular system that we have. And the axis, we increased the number of CTAs that were allocated to each of the cores. And you'll notice as you increase the number of cores, you're going to get more bandwidth. Sorry, the blue line here is the L2 bandwidth. And as you would expect, you would have an increase in the bandwidth. And the other thing you'll observe is that the bandwidth exceeds what the memory bandwidth provides, which is what you would expect. Now, the same applies for the Volta system as well. Now, it takes more CTAs to reach the memory bandwidth, but at a certain point, it would exceed that. So this sort of follows what I was showing earlier in terms of the bandwidth hierarchy here on the left, right now, which is the right thing, which would be the right thing to do. But if you go back to the original work that we did, this is sort of the work, this is sort of the results we get based on the simulations. So we assume the huge memory bandwidth, but the amount of bandwidth or the L2 bandwidth that we can actually get, regardless of what interconnect topology that we assume, is much lower. And again, why is that? It's because of the interface bandwidth assumptions that we made. And the primary focus should have been on the interface bandwidth. And then we should have focused on the bisection bandwidth, not the other way around. So the problem again was that we focused too much on the bisection bandwidth that started off with a baseline that provided sufficient bisection bandwidth. And then we sort of tried to address the problem, but in reality, it should have been the other way around. So again, the problem was we were creating a problem that really did not exist, and then we were trying to solve that. So that was sort of the problem. And here's, again, sort of the summary of what went right. Again, if you look at system performance, system cost, and how the network what role that should play, I think that's the right thing to do. You really should not assume it was a 2D mesh is the right organization. Again, if you redo the analysis that we did and then try to design a mesh, it's going to be a super expensive mesh. That was the analysis that we came up with. And again, this sort of traffic is one of the most critical inputs, obviously, to an interconnection network, but you really need to make sure you're looking at the right problem for a given traffic and for the bandwidth bottlenecks as well. So just to summarize this prior work, again, the key thing is that what you really need to have a good understanding of what it is that you're assuming and have some idea in terms of what impact will the on-chip bandwidth have on what it is that you're looking at. So the key thing, again, is that there is a bandwidth hierarchy across the network on chip, the L2 memory, and you need to make sure that it's properly modeled or assumed in your evaluations. And at the end of the day, it's not the network on chip bandwidth that we care about. It's going to be the overall system performance, and you need to make sure that NoC does not get in the way. So that's sort of a summary of what things that went wrong. And now I'll talk a little bit about some of the additional insights that we've been able to obtain through various different analyses. Now the evaluations will show you some data, but they're really, really simple, straightforward analysis that I think any grad students could do. But I don't think people have really looked at it. So I'll try to sort of present the characteristics and what are some of the limitations, opportunities, and I'll sort of revisit the bandwidth assumptions in the context of multi-GPUs as well. So in terms of GPU, again, all the analysis that we've done is in the context of NVIDIA GPUs, but I think similar observations can be made on AMD GPUs as well. So here's sort of my summary in terms of characteristics of GPU interconnects. Again, I don't have solid answer in terms of how NVIDIA builds their interconnect, but you can sort of guess that it will be built hierarchically, just purely based upon how the cores are organized. Now, like I said before, the expensive resource, again, is the off-chip memory. So you don't want to have the on-chip memory bandwidth being the bottleneck. So that's why you do see hashing being used. And I'll show you some results that sort of demonstrate how hashing is used. Now, when people talk about GPU interconnect, and if they're not assuming a 2D mesh, people assume it's just a single flat crossbar, and they would assume everything is uniform. And what I'll try to show is that it's not necessarily uniform, both in terms of latency and throughput. So again, the goal here is that you should care about system performance and not the on-chip bandwidth or on-chip interconnect performance. So most of you have seen a figure like this from NVIDIA. And if you look at how it's organized, it's done hierarchically in the sense that you have two cores forming a TPC, and multiple TPCs creating what's called a GPCs. So based upon that sort of logical organization, you can assume that the interconnect is going to be some form of a hierarchical. So I drew this sort of as a two-stage, but essentially a muxing of the cores on the first stage and then another muxing at the second stage. The key thing to assume here from the interconnect bandwidth is that this is not a straightforward 2-to-1 mux. This is not a straightforward 7-to-1 mux or whatever it might be. Why? Because if you did that, the bandwidth bottleneck would be severe. So if you're looking at it from a sort of interconnect terminology perspective, the designers of this interconnect would likely have introduced some sort of a speed up. So even though logically it might be a 2-to-1 mux, the performance or the bandwidth slowdown is not going to be 2-to-1. Similarly, if you have a 7-to-1, you're not going to have a 7x slowdown. So this is the assumption we'll make in terms of how the interconnect is organized. But before we dive into the characteristics of the hash, the interconnect itself, let's just look at hashing for a moment. This is, again, the same block diagram that I had earlier. This is the critical resource, right? I'm showing here with the red arrow there, the off-chip memory bandwidth. And the last thing you want is a bottleneck before you get there. So now that could occur based upon your access pattern. So what you'll see in modern GPUs is that they do a very sophisticated hashing to make sure that this does not occur. And again, I think if you Google for hashing, you won't find it. NVIDIA terminology is called it camping. They call it memory camping, and then you'll see maybe 1 or 2 documents that talk about it. But I wanted to first see if this really occurs. And I had my student do just a very simple experiment. So we just had a large address space. This is physical address, and you're just continuously accessing the different regions. And using the performance counters, you can sort of you can figure out which of the 32 channels you're accessing. So if you had something linear, that would be shown here on the green line. So that's what you would hope to have if you had linear mapping of your address to the physical channels. Now, the black are what we're actually observing. Now, the numbers that we get from the performance counters, channel 7 does not necessarily mean it's next to 8. So there's no real significance to that. But what we did for the first 64 of them is we sorted them to see if we can, maybe there is a logical mapping, but that sort of a virtual to physical mapping of the physical channel is not something we're aware of. Even if we did that, we get sort of a broken line shown here on the left. So that, again, that was just sort of the student resorting, shuffling the data across to see if we could have a linear mapping. But if we keep that, and you look at the region from 64 to 128, you see those sort of things being scattered across. So each one of those data points is an address, I think, of 1 kilobyte. So you have essentially 4 kilobytes that are, I guess, sort of linear, but then the next consecutive go off to a different region. And if you were to continuously plot this across a larger address space, this pattern would continuously shift. So you see the impact of hashing. So what does that mean for the on-chip bandwidth? The utilization of the bandwidth in terms of across the different ports is going to be relatively well balanced. So if you're trying to look at congestion, if you're trying to look at sort of various ways of alleviating congestion with routing, that's probably not the right thing to do, right? Because this is what's being done to ensure that the expensive resource here, again, which is the off-chip bandwidth, does not get bottlenecked from the on-chip bandwidth. Now, having said that, I'm going to, pick on Jan's earlier comment, 40 cycles. Is that important? This is the plot here on the top is the latency measurement that my student did from a single core to the various different 32 slices. So in this particular, this was on a Volta system. So there's 32 potential L2 slice destinations. And if you look at the latency measurements, it varies anywhere from 220 to about 260. So there's actually a significant variance. And there's nothing else going on in the system. This is just a simple code that accesses an L2, and we're just measuring the latency. And you'll notice there's quite a bit of variance. This is because of the physical placement of the cores versus the L2 partitions. Now, the part that's interesting is that if we do the same measurements on the core that's placed right next to it, you'll notice the characteristics here shown on the bottom is very similar, right? So if you look at how the latency varies, it's very similar. Now, if you do the same analysis for, let's say, a core that's on a different GPC, you'll notice the latency values will change, but the variance still exists. And if you were to look at, let's say, a single core across all the GPCs, you'll notice there's patterns emerging, right? Some of the cores, again, the two shown here in red, 0 and 6, have very similar patterns. The ones in green follow the same pattern and so forth, right? But the latency difference does exist. For example, if you look at the ones on the top, the variance is actually very small, maybe on the orders of 10 cycles. Whereas the ones on the bottom 2 rows, you'll see on the orders of maybe 40, 50 cycles as well. So these are some of the interesting characteristics that you observe, and maybe these are things that you could exploit if you're looking at sort of scheduling or other aspects as well, right? Again, if you're adding new interesting features, maybe the cores on the top, well, that 40 cycles that you're introducing for your feature could be important. But if you do it right for these cores on the bottom, maybe it's something that you can ignore. Now, this is the latency aspect. Now, let's look at the impact of them in terms of on-chip bandwidth. So in this particular example, you have this core, single core here shown, and it has maybe about a 250 cycle latency. Now, if you run another core on the same TPC, and you do the exact same thing, you'll notice that the latency jumps significantly, almost by a factor of 2x, right? That's, again, because of the fact that those two cores are sharing the same bandwidth into the interconnect. This can be a bottleneck. Now, again, if you do the same analysis with two cores that are on different GPCs, you'll notice that there's essentially no interference between the two. So again, placing two cores, these are very simple synthetic workloads that are just accessing L2s. And you'll notice if you're placed on the same TPCs, you have sharing of the on-chip bandwidth, whereas if you had it on different cores, it's not the case. Now, like I said before, there was hierarchy of the cores across, and if you actually use all the cores within the same GPC, there's some degradation of performance. But you'll notice that the difference or the increase in latency is maybe on the orders of 30, 40%, not what it was back here with almost a factor of 2x. So that's how the on-chip bandwidth hierarchy is designed, in the sense that if you have these two cores, maybe there is quite a bit of bandwidth over subscription. Whereas if you had these sort of 7 cores trying to share the same bandwidth out to the L2, the performance impact is relatively smaller, right? So if we did the same analysis with various reads and write traffic, and as you can imagine, as you increase the number of activated cores you're using, the performance degradation obviously increases as well. So that was sort of the analysis that we've done in terms of what on-chip interconnect looks like. And the question is, can we take advantage of that somehow? So one of the things that we did was, well, can we take advantage of this in terms of security challenges? So one thing we did was, we demonstrated a very high bandwidth interconnect, high bandwidth covert channel, taking advantage of what the GPU provides. So one of the key things is that we have to sort of figure out what the network looks like in terms of the placement of the cores. And so this is what my student was able to figure out using the analysis that I just showed you on the previous slides. I think the interesting part here is that not all the cores were active. So in this particular system that we had two TPCs or 4 SMs that were disabled. So those were not active. But otherwise, you had to reverse engineer. And again, this was just a lot of engineering work to figure out which cores are allocated next to each other, or which cores are physically placed next to each other. And again, this is sort of the high-level block diagram that we're assuming. So when we're designing the covert channel, there was the two resources. There's ones on the top here, where it's the sharing of the cores within the TPC, and then the cores across the GPCs. The attack itself is really, really simple, right? So it's either about whether you're actually using their resource or not. So if you're trying to communicate a bit 0, well, the receiver doesn't send anything, so there's no contention, so you obviously have a low latency. Now, if you're trying to communicate a value of 1, you send something and then you experience a higher latency, right? So that's all that was required. So actually, it was a very, very simple covert channel that could be established of taking advantage of this sort of hierarchical organization. So again, there are 2 levels of sharing. One is at the TPC level, and the second is at the GPC level. So that was exploited to obtain a relatively very high bandwidth covert channel. So again, when people talk about covert channels, if you're getting about a megabit per second of covert channel bandwidth, that's considered high. We were able to, I think, get up to, I think, 24 megabits because of the parallelism in terms of that's available in the GPUs. Now, here's another sort of interesting observation about GPUs. One of the key things about this sort of a covert channel is that we need to synchronize between the senders and the receiver. And that's often a challenge, and that introduces quite a bit of overhead. So, and that obviously eats into your bandwidth that you could achieve. So what was interesting is that we were able to get away without having to do anything fancy by taking advantage of the clock values. It was interesting that the clock values across the different cores are very different, right? There's drifts, and there's also various different reasons why you're never going to get a great synchronization across the cores. But the cores within the same TPC had essentially identical clocks. So they were very synchronized. The other thing is that the cores within the same GPCs were also nicely synchronized. So this was actually a great feature that we were able to exploit for the covert channel. So we didn't have to do anything fancy. We were able to observe that the clocks were doing the job for us. So based upon that, the details, you can find the results in the paper, but we were able to, again, taking advantage of multiple TPCs that's available. I think the maximum bandwidth we were able to achieve is 24 megabits per second. So there's a lot of other sort of interesting aspects of it. I won't go into the details, but refer you to the paper. I think one of the interesting things was that, you know how people say that memory coalescing is an important aspect. Well, that was really bad for us because in terms of establishing the covert channel. So we made sure that coalescing did not occur. And then I think there are many different ways of trying to improve upon the bandwidth of the covert channel itself. So that was our prior work in terms of covert channel. Now since that prior work, we sort of tried to extend it and see if can we take advantage of this. Given that there is vulnerability, can we use this to establish a side channel, which is obviously a lot more serious than a covert channel. So if you have codes written on the right, I don't think this is anything new. A lot of side channel attacks have taken advantage of this. You're doing some work, and based upon the key itself, if it's, let's say, has a value of 1, it's going to do some additional work. And people often try to measure that time to see how many bits of 1s you have. The way we observe the additional work is that because the sharing of the on-chip bandwidth, you're able to see the spike in the L2 latencies, which is what you observe on the top row, versus if you're just having a bit 0, you don't have that spike. So we're taking advantage of the on-chip interconnect bandwidth to establish not only the covert channel, but also the side channel as well. So now, before I wrap up, I'll just talk a little bit about multi-GPUs as well, because I think the bandwidth for multi-GPUs are as critical, especially for these sort of systems that are scaling on. So here I have a picture of relatively old GPU system, DGX. This is one of the Pascal systems, and it had 8 GPUs, and it was interconnected in what they call a mesh cube, right? So each node had 4 links, and it was connected in this sort of fashion. The reason I bring this up as part of this talk is that I think people can get into the same problem if people are stuck on the same metric of bisection bandwidths. So what do I mean? This is the same topology. I just sort of redrew it in a flat fashion, right? Now, again, the bisection bandwidth would be this part where you're partitioning the system in half and where you have the minimum number of channels crossing. So in this case, it would be 4. Now, again, this is just our pure analysis speculation, but I think it's a relatively correct observation in the sense that NVIDIA went from the Pascal system to a Volta system, and they added 2 additional links. So instead of having 4 links, they had 6 links. So each node here would have 2 additional connectivity. So if you were under the mindset that bisection bandwidth is the most important thing, well, you would have designed it in this sort of a fashion. This is what I would have assumed would have given you the higher amount of bisection bandwidth, right? Again, each node has 2 additional channels, and then maybe you add the remaining bandwidth available here shown on the right. So that is what I would have assumed. But this is what happens. This is the connectivity that was provided as part of their Volta DGX system, right? So you see the difference. The bisection bandwidth of what was built is much lower than what could have been built. So I think it's really worth thinking about, well, why did they do that? Now, again, a lot of this is speculation. I think there could have been practical implications. The interconnect design is always impacted by the packaging constraints. So depending upon how these systems are packaged, this could have made a lot more sense versus this organization. But I would argue the real reason is likely because of how the type of communication that occurs, right? Again, bisection bandwidth is important. There's no doubt about that. But do GPUs really care about these point-to-point communications that are often the case for supercomputers, right? The speaker from AMD was talking about sort of collective communications. And if that is an important metric, right, you want to make sure you provide a system that can provide high bandwidth for collective communication, right? So by having this connectivity that's provided in the NVIDIA GPU systems, it actually allows you to embed multiple rings. So in this particular organization, you can actually embed 3 rings. If you count by direction, that's 6 rings. So this gives you 6 rings. If you take this organization that I was showing you earlier, that I said will give you higher bisection bandwidth, you can't get more than 4. That means some of the channels are actually left unutilized if you're trying to optimize for collective communication. So that is where bisection bandwidth, again, it's traditionally an important topic, is maybe not the right metric, especially for these multi-GPU systems, especially that emphasizes, has great emphasis on collective communication. So again, I leave the last bullet here on as well, in the sense I'm sure there might have been some packaging constraints that limit to the amount of bandwidth you can get off of the systems that maybe also made this the design of this much more preferable. So with that, let me just summarize. I think on-chip communications is not a component that really gets exposed. And if it's doing its job, it doesn't get noticed. But if it doesn't do its job, it's always a problem, and it will show up and will make people unhappy, right? So the key thing is make sure you understand what the what impact the on-chip communication has on the system that you're looking at, on the microarchitecture you're assuming. And I would, again, argue that nothing comes for free. People say transistors are free, on-chip bandwidth is free, nothing is free. So it's really important that you come up with a system that is really balanced across all the hierarchy. And then the question that I leave here is that, can you take advantage of the on-chip communication? So we demonstrated a few of that. One of this was the Covert channel side channel packs. Now, there could be different opportunities. For example, if you're trying to schedule a task across the system, which is not uniform, right? I sort of hopefully demonstrated that it's non-uniform based upon the access pattern. Can you do something much more intelligent in terms of scheduling? And if you're trying to introduce new features, can you take advantage of these sort of non-uniform bandwidth latency characteristics? So the last thing here I leave with is that on-chip bandwidth should not be the critical component, right? It is relatively cheaper than the other components, but if it's not properly considered or analyzed, it can be the critical point, and I'm sure that's not what you're looking for. So with that, be happy to take any questions.
Thank you, President. It's a great talk. This video I enjoyed it. I have a question regarding the upcoming like modern chiplet-based architectures that earlier it was like mostly on like on-chip networks. They are building a multi-core architectures, and then they have been the traditional network domain as well. But now this domain of like chiplet architectures, like do you think like the existing wisdom on insights that we got from the on-chip networks are extended, or does it actually require a more innovative approach in order to provide the bandwidth required for the chiplet-based GPUs?
That's actually a great question. I think that your question is effectively, I think some people call it network on interposer. Chiplet-based interconnect, how is that different from sort of traditional on-chip networks? I mean, I don't have a great answer, but some of the thoughts that would go in is that how is that characteristics different from the other systems? At some point, it's actually somewhat in between a network on chip and an off-chip network. So I think that's where it's sort of the starting point. What are the important parameters in terms of cost, right? Some fundamentals of interconnect will not change, right? The fact that hop counts matters, bandwidth matters in terms of performance, that's not going to change. The key part is how do you take advantage of the unique characteristics of that system, as well as what sort of communication pattern are you going to observe on that, right? So are people going to use that as sort of one monolithic system, or is it going to be something different? Or I think the other way to think about it is that can the communication drive what the workload should be, right? I would argue that it's not going to be a flat system, right? So if you have a well-defined sort of communication, how should that impact how people use the chiplet system? I think those are some of the more interesting answers that should be answered than just sort of saying, oh, is topology A better than topology B? Because a lot of the analysis on topology A versus B are sort of the traditional metrics. And one of the things that I mentioned earlier is that we should be thinking more along the lines of sort of what's called domain-specific networks. And what are you going to be using that for, or what can you use? So I think maybe that should be a better starting point. And then after you have that sort of settled down, you should sort of explore what is the right topology. Sorry, I don't have the great answer in terms of what it should look like, but my guess is it would be somewhere in between what a large supercomputer network could look like versus a on-chip network.
Thank you. One more.
Sure.
With the modern like disaggregated tree coming to the picture with like modern protocols like PXL and all those other stuff, do you think going forward like we'll have like heterogeneous network functions as well for different kind of, as I said, like for different communication parameters, domain specific networks? So can there be like an ensemble of these kind of networks going forward in the system?
So I guess your question is sort of, will heterogeneous networks dominate the world? Is that sort of your... A couple of years ago, I had a paper and the title of it was related to unified networks because I wanted to get away from exactly what you were saying. There is the academic aspect and there's sort of the practical industrial aspect. I think having heterogeneous makes sense because from what we learn, well, it's going to optimize whatever we're trying to solve in terms of cost efficiency. From a practical perspective, having 4 different types of interconnects is really not the most efficient way of designing networks, right? I think one of the reasons 2D mesh is a well-adopted organization is that it's homogeneous and it's very simple, right? You can have a single router and you sort of stamp it across. One of the first questions that I got when I was actually interviewing at Intel, they were asking me about the work I've done, and I was telling them how it's great, it's scalable. The question they asked me was, is it extensible? Right? Because they have a first generation, they go to the second generation. If they have to redesign their network every time, right? That is a very added cost, right? If you go from a 6 to an 8 core, you often don't redesign the core from scratch. But if you have to do that for your network, that's something to consider. So I think from an academic perspective, I think we should explore heterogeneous, right? You should explore what the optimal points are. But then you should sort of take a step back and see if is there a much more elegant way of doing this in a sort of I don't want to use the word unified, but a more simplified version. So there's always going to be room for heterogeneous networks, I think. But again, there is an overhead, both from sort of the cost of designing and implementing such networks.
One question. So I see your pyramid diagram, and also I think you're advocating for a more balanced design, right? For the L1 cache, L2 cache memory bandwidth. So it's definitely achieve the bandwidth. The bandwidth will definitely be different, right? L1 cache will definitely have higher bandwidth than L2 cache. So I think the question is, it really depends on the workload. So how much do you think the workload specific network design or somehow programmable network design should be taken into consideration?
Sorry, so the question is, how much should the workload characteristics be taking into account?
When you design this type of balanced network system?
I don't know if there's a great answer. Like there was one comment earlier, I think it was sort of about achieving the most cost-efficient solution, right? Again, L1 bandwidth is obviously a lot cheaper. But again, if you have increased that by a factor of 1,000, right, it's going to add up and it's going to exceed the other components as well. I mean, I don't have the great answer in terms of what is the right design. Again, it will depend upon the workload. That's obviously an important aspect. But the key thing, I think, is that what is the most expensive resource? I think it starts from the memory. And you definitely don't want to bottleneck it anywhere in getting close to it, right? You want to be able to fully utilize it, and then you sort of work backwards. Now, obviously, some workloads are not going to use the memory intensively. It's going to be much more, let's say, L1 or L2 intensive. And for those, maybe you do want to increase it. So maybe the right design is not a hierarchy, but maybe it's more of a step function that provides a little more bandwidth as you go down the hierarchy. But in terms of what is the optimal, I'll let you figure that out.
Just want to follow another question regarding multi-GPU system. So this type of balanced design is more likely to have an on-chip, right, for on-chip connection, right? Probably the on-chip bandwidth will be the most high resources. And then do you think the design philosophy, design practice should change because of these the differences?
So I think there's two ways to answer that. One is, how is it practically done? I would argue people would put as much bandwidth as they can physically put within their limits, and then see what you can do with that. In terms of how you would sort of design the off-chip, I'm not sure if I have a great answer to that. I think you could always have a workload that's very hierarchical. Maybe, and that's where you should start off. We have a lot more communication limited to within a chip, and then the amount of bandwidth you get is obviously lower if you go off chip. But if you could envision something that's much more different, for example, if you're going with optics and you have this sort of a very flat bandwidth across 1,000 GPUs, right? What could that enable, right? If that could enable a new type of application, new type of workloads, maybe that's a great starting point, and then you work backwards. Right, so I don't want people to think, well, interconnect is a bottleneck, so you need to think in this particular way. I think you should sort of think in the other way and says, what's possible, what can be enabled, and then see what are some of the practical limitations, right? Like I said before, interconnect is one of the very few aspects of architecture that's not one of the few, but it's dominated by the technology. Technology in terms of what you're putting it on, in terms of physical packaging, in terms of how much bandwidth you can get. But there's a lot of interesting tricks that you could play with the architecture such that you could approach what you would like to have.
I have one more question regarding the multi-GPU network.
Yes.
that it's important to embed as many rings as possible and like as many all reduced rings as possible for the multi-GPU network.
Mhm.
And I believe the option network, like especially NVLinks, are reconfigurable after the already with the system. If that is true, do you think there is an opportunity for training your option network, specific to your whatever application you run,
That's a good question. Actually, the first part, maybe we can talk offline. I'm not sure what sort of reconfigurability is provided. But one of the problems, so I think there's two types of collective communications that people often care about. One is all reduce and the other is all to all. Something that's optimized for all reduce is not necessarily optimal for all to all, because all to all often means that you want to minimize the diameter as much as possible. And all reduce, that's really not the case, especially if it's a ring-based all reduce. You want to maximize the bandwidth. So the short answer is I would argue that there could be opportunities, especially based upon if you have a workload that's much more dominated by all to all versus all reduce. I think there's opportunity, but how that's done, I guess that's sort of the tricky part. Now, sorry, this is sort of a separate topic, but it relates to what you talked about in the sense, recent work from Google has talked about sort of optical circuit switching and with reconfigurable organization. And that I think sort of goes along to what you're talking about in terms of reconfiguring the interconnect for the given topology, for a given communication pattern makes a lot of sense. The question that needs to be answered is, well, is it worth it, right? In terms of the overhead of reconfiguring and any costs associated with that.
We ran out of time. Thank you.